we present GraspXL, a method to generate grasping motions for more than 500,000 unseen objects. In our daily lives, we engage with a large amount of objects. In particular, like the infant here, we can grasp objects of any shape without object-specific training. We can also grasp objects with specific motion objectives in mind. For example, grasping an apple from a direction or handing a knife by its grip to cut the apple. Therefore, the ability to grasp general objects according to motion objectives is important for fields like animation, mixed reality applications, and robotics. Motivated by this, our goal is to generate grasping motions for objects while satisfying motion objectives. In particular, we want to generate grasping motions for large scale of objects according to different motion objectives and with different hand models. Our motion objectives are specified by the combination of a graspable area on the object, wrist rotation, heading direction, and hand position. There are two main challenges to generate objective-driven grasping motions at scale with different hand models. First, to generalize across different objects, diverse motion objectives, and hand models, our formulation cannot assume a specific object shape, motion pattern, or hand morphology. Second, the task requires the model to learn how to grasp the object stably while satisfying multiple objectives. This is difficult because the exploration of objectives may flip the object and lead to a failed grasp as shown here. To avoid this, the policy may tend to learn a stable grasping that is inconsistent with the objective and then get stuck in such local optimus. To address these two challenges, we present GraspXL. We formulate the problem with a reinforcement learning framework in a physics simulation. We propose a general framework which can generate multi-objective driven grasping motions for more than 500,000 unseen objects and different dexterous hands. To encourage the policy to adhere to multiple objectives, we introduce objective-driven hand guidance, a technique that guides the hand wrist towards the target pose for faster objective exploration. To adapt to different hand models, we introduce a general reward function composed of two parts, one to encourage stable grasping and the other to encourage following the objectives. Note that our reward is agnostic to hand and object models. See our paper for more details. To generalize to diverse object shapes, we use distance sensors similar to Manipnit to encode object geometries. To enable efficient learning of stable grasping and motion objectives, we introduce a learning curriculum. Specifically, we first train the policy with the objects fixed on the table and apply a larger objective reward. In this way, the policy can focus on learning precise finger motions to complete the objectives without worrying about flipping the object. We then fine-tune the policy with non-stationary objects and a larger grasping reward so that the policy can learn stable grasping. To evaluate our method, we utilize three different object datasets: ShapeNet, PartNet, and ObjectVerse. Here we compare with Syn2R on the left with ours on the right. Syn2R achieves grasping motion generation by first generating grasping poses with an expensive optimization procedure. Then the reference poses are used to guide the generation of the grasping motion. Syn2R suffers from noisy references, and the motion does not exactly follow the reference poses. These factors sometimes make the policy completely fail to grasp or successfully grasp the object, but does not follow the given objectives. In contrast, our method can grasp the object stably while adhering to the objectives without the reference. We further evaluate the generalization ability of our method. Our method can generate motions for 500,000 objects in the object-verse dataset. Our method can reliably grasp the objects and precisely follows the objectives. Here we show that our method can generalize to generated objects from off-the-shelf text to 3D generative models such as Dream Fusion, and reconstructed objects from in-the-wild videos using video-based reconstruction methods such as HOLD. We can also generalize to different hand models with minimal modification of our pipeline. Furthermore, given the same object and hand model, we can generate diverse grasping motions according to different objectives. Refer to our paper for quantitative evaluation. In summary, we present GraspXL, a general framework that can generate objective-driven grasping motions for more than 500,000 objects without relying on any 3D hand object data. We introduce objective-driven guidance and a learning curriculum to handle the controlled difficulty imposed by the diverse objectives and the requirement for stable grasping. We show that our method can generalize to out-of-distribution objects such as reconstructed or generated objects. Different dexterous hand platforms with diverse morphologies and different objectives. Our code will be available for research.